Okay, in the previous sessions we have seen the fluoride and anti-fluoride structure, and that was the simple difference of exchange of cations and anions from fluoride to anti-fluoride structure. And here we are going to see the rutile structure, rutile, R-U-T-I-L-E, rutile structure. And you can see how the box is represented. So the difference between every other structure will be these lengths, the lengths, for example, you have this particular length as A, and then this particular length as B. In some cases A will not be equal to B, and in some cases A will be equal to B, and even this will be equal to C. So in some cases A will be equal to B equal to C. You get a very good cubic pattern, and it all depends on the number of size of the atoms that is there. Suppose if you have, this is an oxygen atom, it may be smaller. If you substitute the oxygen atom by means of a chlorine atom, it becomes larger, and therefore it expands. And that expansion, it increases the length of this lattice, or the length of this parameter, from which is A is not equal to B. So here you can see that titanium is represented here. You have to draw a rectangular box, and you have to construct a cuboid, right? So cuboid should be there, and in all the corners you should have titanium. This one, this one, this one, this one. You can see the titanium in 4 edges. Okay. So after drawing 4 titanium edges on one face, another face, you have got 2 faces in the cuboid. In the center, you have to put one more titanium there, right? So after putting this titanium, oxygen atoms have to be placed octahedrally. Oxygen atoms have to be placed octahedrally. So these are the important point there, and you have to draw the structures. How the oxygen atom is placed octahedrally? You can see this. This titanium is at the center. Okay, this is titanium, right? This titanium, and it is surrounded by, on the top layer you have to. This is the top layer there, right? On the top layer you just have to put 2 oxygen atoms. These 2 are the oxygen atoms. Okay. So likewise in the bottom you have to put 2 oxygen atoms, and in the side which is smaller, this one is larger. Let me tell you that this is what I have taken. This is B and this one is A. So A is not equal to B, and B is larger than A, and therefore where there are large, you have to take 2 oxygen atoms. Where there is small, you have to take only 1 oxygen atom there. So after drawing these oxygen atoms, you can see that I can draw a connectivity triangle like this. Okay, so I can even draw a connectivity triangle like this. And you know what happens? 2 triangles in opposite directions, one like this and another one like this, quite opposite. So I often told you how this goes. And if you see from the above, you see this as a kind of overlapped triangle there. Once you see this overlap triangle, you can simply join these, right? You simply join this, and you will see an octahedra there. So this becomes an octahedra, and that is the octahedral pattern. This is the octahedral arrangement. Okay, so from 2 triangles, but if you should also remember that if 2 triangles are in the same way, you cannot get an octahedra. You will just get a square prism like this. So we have seen that case also in the beginning, how to construct the triangles there. So let us see what is there. The best example they have taken is that of the titanium dioxide. So some of the crystals are based on the parent structure, and titanium dioxide is the parent structure for this as the mineral rutile. So that is how you see this rutile as being the titanium dioxide structure. The ionic radius of titanium is 0.745 and that of oxide is 1.26 angstrom units. That is, oxide ion is larger. The radius ratio of radii to the cation is R equal to 0.745. I think we see in the last class we saw if it exceeds greater than 0.591, the crystal packing changes. So with a radius ratio of about 0.59, the cubic holes are too large. Cubic holes are too large. Therefore, R whole by R minus is 0.732 to be suitable for titanium ions with prefer octahedral. Therefore, the titanium ions will prefer have to be octahedral holes. What are the octahedral holes? I think we have drawn these holes, in the three circles that you have. You can put the third circle above. So I think I have drawn this earlier. So I'm just going to put again some three circles, and here is another circle, and here is another circle there. So you can see a hole that is there. For this particular hole will be called as the octahedral hole in close packed structure. And nature chooses to pack the oxide ions in rutile in oxygen close packing structure. Note how the oxide ions lie in expanded hexagonal close packed structure. So you have to see this one. What oxide close packed structure? HCP. So where do you get this HCP? I think you have to see this arrangement. I'll just take up this. So I'm coming to this. I think you will see that if you have two layers, this is one cuboid, the first cuboid that we have seen. This is the first cuboid. What is in the cuboid? Cuboid is an octahedral pattern you have seen in the beginning of this class, so it is making a change there. So I'm going to undo that. So the lengths are larger. Okay, so I'll draw again, because unless you draw, you will never learn the structures. But remember, drawing of structure is very interesting aspect. So we saw this one like this. This is a cuboid. So we just join them, and I told you to put the oxygen atoms here and here too, and here only one oxygen atom. So this is the oxygen atom there, right? And this one is this oxygen atom there. When you have two oxygen atoms at the top surface and two oxygen atoms at the bottom surface, I'm just putting one dot there, and two oxygen atoms on opposite sides. Here this is quite close to this. In the smaller side, you will have two oxygen atoms, and you can see that we are just joining them to get a octahedral. So that is what is being mentioned there as an octahedral hole. These two triangles, if you see from the top, will give you the octahedral. But what is more interesting is the packing. Two such cuboids, here is one cuboid and here is another cuboid. Two such cuboids can give rise to an hexagonal close packed structure like this. So you see a hexagon there. So this hexagon is what is being mentioned there. So unless you join two or three layers, you are not going to get the because here is the layer of that. The oxygen layer is larger and titanium is very small. So you can see this. So always you are at your liberty to draw a hexagon. You can connect a few atoms and see how they are connected. So I'm able to draw a hexagon there. So in this hexagon, and I'm also able to using these oxygen atoms. These oxygen atoms you have seen are occupying these octahedral holes. So what is an octahedra there? Octahedra is entirely different thing here. So first three triangles there, and then the next three triangles here. Okay, these two triangles are opposite, and in between you have got the titanium atoms, right? So this is the hole that is there, or this is the hole. This is the hole that is there. So in between that is occupied. So but main thing about TiO2 is that it is a rutile structure, but it has got a beautiful structure like this. You have to draw this structure. This is very important for you. And just going to read up that and end up and go back to the next Woodside structure there. So we see how hexagonal close packed structure is there. The titanium pins, which are smaller than oxide ions, are inserted into the octahedral holes. There you saw this. This is the titanium ions, and they are inserted into the octahedral holes and push the oxide ions apart so that the next oxide is in contact with each other. Two oxide ions are in contact with each other means now here it is telling like this. Two oxide ions. Okay, and the unit cell for rutile however is based on the titanium 4 ions and not the oxide ions. Tip the unit cell and this to more clearly observe the packing of the oxide ions. So this is a diagram which I am not able to explore, but you can omit that point also. But you can mention that octahedral close packing, that is the octahedral hole, titanium ions. That is how you have to remember. And then the unit cell contains two layers of oxide ions, three ions in each layer. So the rutile structure has 6:3 coordinations. So 3 titanium. Okay, rutile structure has two layers of oxygens with three ions in ox. Two layers, and each layer having three oxygen atoms. Okay, therefore it is having 6 oxygen atoms. And each layer has got a the rutile structure is observed that tetrahedral loads are occupied by these. So each three will give rise to a void. That void we are calling it as the octahedral hole, and 6 oxygen atoms. You be placing three titanium oxygen. So 6:3 will be something like 2:1. So it's a MX2 type crystal, but it starts from the cuboid. And two layers of oxide ions with three layers each layer, and within two layers you got one titanium being put in the. This is the first layer. How you have to mention the first layer is just a minute. First layer. This is the layer, first layer there. So in the first layer you have got all those things, but if you see it from the top you can change it. So here it is mentioned as the empty octahedral site. Empty octahedral site. Okay. So if they ask you write brief about the structure, you have to draw this structure, write some points about this, and then finally draw this structure. Okay. And this is the rutile structure. Two axes are equal and the third axis is shorter. I will give the notes in the description section. And the metal atoms, they occupy the corners with the additional atom in the center. The metal atoms thus constitute a distorted body-centered cube. Each metal atom is surrounded by 6 oxygen atoms, and that is what we are seeing there. Each oxygen atom is surrounded by 3 metal atoms. So 6:3 is the metal oxygen coordination, and some compounds, they have that stoicheometry, that is AB to stoicheometry, conform to examples can be cadmium iodide, but it has got threefold coordination and do not occupy the corners of equilateral triangle. In the cadmium iodide we have already seen. This is a calcium chloride, has a similar structure there. Calcium chloride has a similar structure. Now coming to the Woodside structure, this is an example that is taken from the zinc sulphide. As you can see that zinc sulphide is there on the left side here, and then you've got Woodside on the right side. The Woodside crystal structure. So this is about Woodside. Is referred by it's a German name there. A designation, the person the symbol is also given there. But I'm just given this. I copied from a website, but you can just ignore it. You look into the notes that I'm giving there. Among the compounds that can take up this Woodside structure, so here or the Wurtzite is the zinc sulphide at about 8% of iron instead of zinc. Silver iodide is an example. Zinc oxide is an example. Cadmium sulphide, cadmium selenide, silicon carbide, gallium nitride are there. Look at how this structure in the zinc sulphide exists in the Wurtzite structure and can have zinc blende structure. Both are same. It's a very binary compound with the stoicheometry of the type AB. And the sulfur atoms, you can see where are the sulfur atoms there. Uh, just a minute, I'll write the sulfur atoms are these are the sulfur atoms. These are the sulfur atoms there, and this is the zinc atom there. And the sulfur atoms are arranged in hexagonal close pack. Sulfur in SCP. So when you see a cuboid, this is a cuboid. This length is larger and this is shorter. You see a cuboid, you can see that it can be placed in hexagonal also. How two cuboids can give rise to one hexagon is what we have seen here. We place two cuboids there, one cuboid here, another cuboid. Cuboid 1, cuboid 2. And these two cuboids, the center can make a hexagon there, right? This hexagon. And this hexagon which I have drawn is what this hexagon is also meaning when you arrange them in such a pattern. So here you have this hexagon, right? This is a hexagon. So this packing, this kind of arrangement we call it as the hexagonal close packing. The sulfur atoms are rearranged. So you have these sulfur atoms there. And zinc atoms occupy half of the tetrahedral sites. That is the tetrahedral site. So if you have three circles there, sorry, just to draw a good circle there. It's not after doing it, so I'm just again drawing this. So you got three circles. So when you draw three circles and place a fourth one on top of these three circles exactly instead of placing on a distorted thing, you get a hole like this at the center. This, okay. This particular vacant place we call as the tetrahedral hole. Okay, so here you have to remember zinc atoms. Zinc atoms are placed in the tetrahedral hole. The layers of the sulfur atoms will thus be, because it is AB, it will go like this, AB, 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 like that it will go. And the coordination number is therefore 4:4. Because every 4 sulfur atoms, you'll have, for every 4 sulfur atoms in a layer, you will have 4 zinc atoms. That is the coordination number. Each zinc atom is surrounded by 4 sulfur atoms. Similarly, each sulfur atom is surrounded by 4 zinc atoms. And the bottom unit has therefore 7 layers. Which is the bottom unit? I'll just put the bottom unit there and explain what exactly is meant by that. So this is the bottom layer. 1, 2, 3, 4, 5, and 6. So you can see this. We've got 1, 2, 3, 4, 5, and 6. Okay. And the center is also having one more. Center is also having one more. This one is the seventh layer, seventh atom. And in the seventh atom, this layer is there. So this particular thing, is slightly raised. And here you can see that which one is raised. Can you just make out? This is not raised. This is slightly raised. This one. Okay. I'll draw exactly this one there. Put this atom here like this. And draw a line like this. And the red circle. Exactly this. And then I'm going to put the other things like this. So I'm drawing them in blue. This is this. This one is this, and the seventh one is this one. Okay, so you get a very good tetrahedra there. Very good tetrahedra there. Or you can just join these three lines and draw something like this. So you know very well how a tetrahedra is drawn. That, that you get it. This is the tetrahedra. And the bottom layer has got 7 units, and second layer from the bottom has got the seventh atom as zinc, and the third layer from the bottom has got 3 atoms of sulfur. So bottom layer sulfur. From the bottom, the next layer is having zinc, and then again sulfur, and then fourth layer has got zinc. So therefore, the top layer has got 7 atoms, out of which all these are zinc. All these are zinc. That is the Wurtzite structure. So two two such structures can give rise to this hexagonal close packing. And the thing is, here it is. This is a very beautiful drawn structure of the HCP structure. And now you can see the tetrahedra there. This, and this is for 1, 2, 3, and 4. 1, 2, 3, 4 give rise to tetrahedra there. And this 1, 2, 3, 4, 5, 6 gives rise to 1, 2, 3, 4, 5, and 6 gives rise to SCP hexagonal packing. But the seventh one atom is also there. This is also the same element, that is zinc. And then you got the 7 atoms there in the first layer. 7 atoms in first layer. The next layer is that of the next atom is zinc. So it has got 3 atoms there. 1, 2, and 3. This is the next layer there. Okay. So 1, 2, and 3 forms the second layer. Okay. Then come to this. Here you will have 1, 2, 3, 4, 5, 6. So this 1, 2, 3, 4, 5. One more will come here. That is not drawn there. So zinc, sulfur, zinc, sulfur, zinc, sulfur, like that it will keep on moving. And you can see how this tetrahedra can be drawn there to represent the structure. So for more details, you can just look at the description of the atoms there. But in the examination, you have to draw the diagram. That is very important there. Thank you for joining me, and see you soon with some other structures.